Welcome to this explainer. Today, we're diving into something that is literally upending the traditional physics classroom: interactive virtual labs. If you're an educator who is, frankly, tired of watching students glaze over at the sight of complex chalkboard equations, or maybe an edtech enthusiast looking for better ways to bridge the gap between theory and reality, you're definitely in the right place. Let's see how moving science into a digital world changes the whole shebang when it comes to teaching and learning.
It's a great question, isn't it? Think back to trying to fully grasp a concept of momentum just by staring at a static equation. It's a universal struggle. It often leaves the science feeling completely invisible and honestly entirely disconnected from the real world. But what if you could manipulate those invisible forces with your own hands, digitally, from anywhere? Let's kick things off with Section 1, Beyond Static Textbook Physics. Because, let's be real, traditional physics relies way too much on static diagrams. Concepts like momentum feel entirely abstract. It's rarely something you can just easily observe in a textbook. Without interactive elements, it's incredibly tough for anyone to see how energy transfers dynamically from one object to another. And let's be honest about physical labs for a second. Setting up these experiments in the real world, it's expensive, it's time-consuming, and almost impossible to recreate perfectly every single time. A warped track, a broken photogate, or slightly misaligned equipment can literally ruin an entire lab session. It leaves instructors frustrated and students completely confused when their data doesn't match the theory.
Which brings us to Section 2, Visualizing Core Momentum Concepts. Take a foundational concept like linear momentum. We all know the drill, mass times velocity, right? But just reading that is one thing. Experiencing it is a total game changer. In this virtual space, students don't just crunch numbers, they directly interact with them. By just dragging a slider to change the mass or velocity of an object, they see the momentum shift in real time. They can pit a light, fast-moving object against a heavy, slow-moving one and immediately visualize what happens. It takes a static, boring variable and turns it into a tangible, memorable cause and effect relationship.
The exact same logic applies to the conservation of momentum. In a regular classroom, you often just have to blindly trust the math that total momentum stays constant in a closed system. But here, you're the one running the trials. You can tweak the starting conditions endlessly, mess with the friction, adjust the mass, and watch the math definitively prove itself right before your eyes. It perfectly bridges that gap between theoretical math and practical reality.
And when we're talking about modeling collisions, the visual feedback is simply night and day. You can instantly toggle between elastic and inelastic scenarios. So instead of just reading a bullet point that an inelastic collision loses kinetic energy to heat or physical deformation, the simulation actually models that energy loss. You visually see the objects crumpling or deforming right there on the screen. It makes the distinction instantly concrete.
Now, this real-time visual feedback is especially crucial for a nuanced concept like impulse. By showing exactly how a force applied over time changes an object's motion, the software brilliantly illustrates how a small force applied briefly produces the exact same effect as a larger, instantaneous force. Actually, peer-reviewed research heavily backs this simulation-based approach, specifically because it takes those heavy cognitive loads and lightens them through immediate visual proof.
So why does all this virtual testing actually matter? Well, because it connects to the real world. We're talking about the life-saving engineering behind vehicle airbags, how modern car crumple zones absorb crash impacts, or even just the mechanics of a baseball bat striking a fastball. Connecting these theoretical formulas to familiar everyday situations really helps students retain the principles long after they log off. It proves that physics isn't just trapped on a chalkboard.
Moving right along to Section 3, How Virtual Collisions Work.
The true beauty of a virtual lab is the totally frictionless workflow. First, you set your variables, like mass and initial velocity. Next, you run the simulation. Finally, you observe the instantly calculated outcomes. Because the software handles all the tedious manual calculations behind the scenes, you can focus purely on analysis and critical thinking. If you suddenly wonder, hey, what happens if I quadruple the weight? You can test that chaotic scenario safely in mere seconds. It heavily encourages rapid trial and error.
Let's look at this in action with PraxiLabs, a huge innovator in this space. Take the classic ballistic pendulum experiment. You virtually fire a projectile, measure the deflection angle, and work backward to find the initial velocity. Or, with Newton's second law, you can isolate specific variables in ways that are incredibly finicky to pull off in a physical lab. By comparing results across dozens of rapid-fire runs, you start to uncover mathematical patterns that you'd completely miss in a single textbook example.
Let's dive into Section 4, the PraxiLabs Advantage. What makes this platform really stand out for institutional adoption is just how comprehensive it is. Take the Oxi AI Lab Assistant. It offers real-time, personalized guidance. It's basically like having a private tutor looking right over your shoulder whenever you get stuck. For teachers, there are custom quiz builders tied directly to the experiments and seamless LMS integration with platforms like Moodle or Canvas that gets up and running in under 24 hours. Throw in bilingual support in English and Arabic and 24/7 assistance, and it is a massive empowerment tool for the modern classroom.
And for educators and admins, the benefits are just as impressive. You get automated real-time tracking and highly detailed reports that flag exactly where someone is struggling. Plus, let's not overlook safety and budget. Giving every student access to an instantly resettable lab means they can explore costly or even physically dangerous scenarios with absolutely zero risk of injury or broken equipment. It's a clear, documented return on educational investment.
To really understand where the broader educational landscape is heading, just look at this number, 8.57%. That's the projected compound annual growth rate for virtual reality in the education sector heading into 2030. This isn't just a fun, futuristic gimmick anymore, folks. Simulation-based STEM learning is rapidly becoming the global standard. Forward-thinking institutions realize that to keep digitally native students engaged, you absolutely have to meet them where they are, inside interactive, responsive environments.
Which leaves us with one final critical question. Will your students continue to just passively memorize formulas on a chalkboard, or are you ready to let them truly experience physics? Institutions that adopt these virtual simulations early are going to see the fastest gains in student engagement and long-term comprehension. It's definitely time to rethink how we bring science to life. Thank you so much for joining me for this explainer, and keep exploring the incredible potential of virtual labs.